Hey everyone, and welcome to Time Pilgrimage. Did you know that scientists have built a machine so large it can circle nearly 17 miles underground? That's like running a marathon around a giant science experiment. This isn't science fiction, this is the Large Hadron Collider, or LHC for short. The LHC is the largest and most powerful particle accelerator ever built. Located at CERN in Switzerland, this incredible machine smashes tiny particles together at near the speed of light. Why? Because by doing so, we can recreate conditions similar to those just after the Big Bang. Think about that for a second. We can recreate the very moments our universe was born, right here on Earth. It's like looking back in time to the beginning of everything. This groundbreaking research has the potential to unlock some of the biggest mysteries in the universe, including the nature of dark matter, the existence of extra dimensions, and maybe even the secrets of time travel itself. So buckle up, because we're about to dive deep into the fascinating world of the LHC. Now, I know what you're thinking. Time travel? Isn't that just for sci-fi movies? It's true that time travel has long captured our imaginations, but the science behind it is more intriguing than you might think. At its core, time travel is about manipulating the very fabric of the universe, space and time. Einstein's theory of relativity suggests that time is not absolute but is relative to the observer's motion and gravity. So where does the LHC fit into all of this? Well, by smashing particles at such high energies, the LHC allows us to study the fundamental forces that govern the universe, including gravity. These experiments could potentially reveal hidden dimensions or particles that interact with gravity in unexpected ways, potentially opening doors to understanding how time travel might be possible. It's still early days, but the LHC is giving us a glimpse into the fundamental laws of physics that might one day allow us to manipulate time itself. Before we go any further, let's clear up some common misconceptions. The LHC is not a time machine in the traditional sense. We won't be hopping into DeLoreans and traveling to different eras anytime soon. Similarly, time travel itself is often misunderstood. Popular culture often portrays it as a simple jump through time, but the reality is likely far more complex. The laws of physics as we understand them present significant challenges to time travel, including paradoxes and the potential for unintended consequences. However, exploring these challenges is crucial to advancing our understanding of the universe and the nature of time itself. So, while the LHC may not be sending us back to the dinosaurs just yet, it's helping us unravel the mysteries of the universe, and that includes the tantalizing possibility of time travel. To truly grasp the potential of the LHC and its connection to time travel, we need to venture into the bizarre world of quantum mechanics. This realm of the very small operates under rules that defy common sense. Here, particles can exist in multiple states at once, and the act of observation itself can influence the outcome of events. Imagine a world where a single particle can be in two places simultaneously, or where information can seemingly travel faster than the speed of light. This is the reality of the quantum realm, a place where the fundamental building blocks of our universe dance to a different tune. The LHC allows us to peek into this strange and wonderful world by smashing protons, the hearts of atoms, together at nearly the speed of light. These collisions generate a shower of subatomic particles, each carrying clues about the forces that govern the universe. By studying these particles and their interactions, we can begin to unravel the secrets of the quantum realm and its implications for time travel. Think of it like this. If we want to understand how a car works, we need to take it apart and examine its individual components. Similarly, by smashing particles together, we are essentially taking apart the universe to understand its fundamental building blocks. Our current understanding of particle physics is encapsulated in what we call the Standard Model. This model describes the fundamental particles of matter and the forces that govern their interactions. We have the fermions, like electrons and quarks, which make up the matter we see around us. And then there are the bosons, like photons and gluons, which mediate the fundamental forces. The LHC plays a crucial role in testing and refining the Standard Model. By observing the particles produced in these high-energy collisions, we can verify the predictions of the model and search for new undiscovered particles that might lie beyond its current scope. One of the most significant discoveries made at the LHC was the Higgs boson, a particle responsible for giving mass to other particles. This discovery filled a crucial gap in the Standard Model and earned Peter Higgs and Francois Englert the Nobel Prize in Physics in 2013. But the story doesn't end there. The LHC continues to push the boundaries of our knowledge, searching for evidence of new particles and forces that could revolutionize our understanding of the universe and potentially even unlock the secrets of time travel. The discovery of the Higgs boson was a monumental achievement in particle physics, confirming a key prediction of the Standard Model and providing crucial insights into the origin of mass. But its significance goes even further, potentially holding clues to the nature of time itself. Theoretical physicists have proposed that the Higgs field, which gives rise to the Higgs boson, might be connected to the fabric of spacetime. Some even speculate that manipulating the Higgs field could potentially warp spacetime, creating shortcuts or wormholes that could allow for time travel. Think of spacetime as a sheet of fabric. Massive objects like stars and planets create indentations in this fabric, much like a bowling ball placed on a trampoline. These indentations represent gravity. Now imagine if we could manipulate the fabric of space-time itself, creating tunnels or shortcuts between distant points. This is the essence of wormhole theory, a concept that has captured the imaginations of scientists and science fiction writers alike. While manipulating the Higgs field remains firmly in the realm of speculation for now, the LHC provides us with a tool to study the Higgs boson in unprecedented detail, potentially revealing hidden connections between the Higgs field, gravity, and the very nature of time. We experience the world in 4 dimensions: 3 spatial dimensions, up, down, left, right, forward, backward, and 1 dimension of time. However, some theoretical models, such as string theory, suggest that our universe could have many more dimensions, curled up and hidden from our perception. These extra dimensions, if they exist, could hold the key to understanding the fundamental nature of gravity and its relationship to the other fundamental forces. Some theories propose that gravity might be leaking into these extra dimensions, which could explain why it appears so much weaker than the other forces. The LHC could potentially provide evidence for these extra dimensions by producing particles that interact with them. Imagine if, during a collision, some energy seems to disappear. This could be a sign that the energy has escaped into an extra dimension, leaving behind a telltale signature. The existence of extra dimensions could have profound implications for time travel. If we could access and manipulate these hidden dimensions, we might be able to find shortcuts through space-time, effectively bending the rules of time as we know them. The concept of time travel is riddled with paradoxes, seemingly impossible situations that arise from the ability to travel through time. One of the most famous is the grandfather paradox. What would happen if you went back in time and accidentally killed your own grandfather before your parent was born? This paradox highlights the potential for causality violations, where an effect could precede its cause. If you prevented your own birth, how could you exist to travel back in time in the first place? These paradoxes are not just thought experiments. They expose the potential logical inconsistencies that arise when we try to reconcile time travel with our current understanding of physics. There are a few proposed solutions to these paradoxes. One possibility is the Novikov self-consistency principle, which states that while you can travel to the past, you cannot change it. Any attempt to alter the past would be met with self-correcting mechanisms that ensure consistency. Another possibility is the existence of parallel universes or alternate timelines. In this scenario, traveling to the past might transport you to a different version of reality, allowing you to make changes without affecting your original timeline. The concept of parallel universes offers a fascinating solution to the grandfather paradox and other time travel conundrums. Imagine a multiverse where every possible outcome of every event branches off into a separate, self-contained timeline. In this scenario, traveling back in time wouldn't alter your own past, but would instead transport you to a parallel universe where the events you attempt to change have already unfolded differently. You could meet your grandfather, but it wouldn't be the same grandfather from your original timeline. This idea of a multiverse, while still highly speculative, has gained traction among some physicists as a way to reconcile quantum mechanics with our understanding of the universe on a larger scale. The idea is that every time a quantum measurement is made, every time a particle chooses one path over another, a new universe is born, each representing a different possible outcome. In this grand cosmic tapestry, every possible version of reality could exist simultaneously. While we are a long way from proving the existence of parallel universes or developing the technology to traverse them, the LHC's exploration of the fundamental laws of physics could provide us with clues about the true nature of time and the possibility of alternate realities. Imagine time not as a straight line but as a flowing river, constantly moving and changing. At the quantum level, this river becomes a turbulent stream, full of eddies and whirlpools. This is the realm where the very nature of time becomes fluid and uncertain. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, suggests that time itself might be subject to the same strange rules that govern the quantum world. Just as a particle can exist in multiple states at once, could time also branch into multiple possibilities? Some physicists believe that the key to understanding time travel lies in unraveling these quantum mysteries. If we can understand how time behaves at the most fundamental level, perhaps we can learn to manipulate it, to navigate its currents, and even bend its flow. The LHC, with its ability to probe the quantum realm with unprecedented precision, could hold the key to unlocking these secrets. By studying the behavior of particles at the highest energies, we might catch glimpses of time's quantum dance, revealing the hidden mechanisms that govern its passage. Wormholes offer near instantaneous travel across vast distances, even through time. Are these shortcuts real or just science fiction? Einstein's theory suggests massive objects warp spacetime, creating gravity. Imagine a bowling ball on a trampoline causing it to sag. A wormhole is like a tunnel connecting two distant points in spacetime. Stabilizing wormholes requires exotic matter with negative energy density. Imagine the fabric of spacetime not as a smooth, continuous sheet, but as a turbulent sea of quantum energy, constantly fluctuating and bubbling with virtual particles popping in and out of existence. This is the concept of quantum foam, a realm where the very nature of space and time becomes uncertain and unpredictable. At this subatomic level, time itself might be subject to these quantum fluctuations, jittering and shifting like a flickering candle flame. Some physicists theorize that these temporal fluctuations could, under the right circumstances, allow for the formation of tiny, transient wormholes connecting different points in time. Think of it like this. Imagine a vast ocean with waves constantly crashing and churning. Occasionally, two waves might collide in just the right way to create a momentary bridge between them. Similarly, in the quantum foam, random fluctuations in spacetime could create fleeting connections between different moments in time. While these temporal wormholes would be far too small and short-lived for human travel, their existence would have profound implications for our understanding of time itself. The LHC, by probing the quantum realm with unprecedented energy, could potentially provide evidence for these temporal fluctuations, offering glimpses into the chaotic dance of time at the smallest scales. Black holes, those enigmatic objects of immense density and gravitational pull, have long captured the imagination as potential gateways to other universes or even time travel machines. But could these cosmic behemoths truly hold the key to unlocking the secrets of time? Einstein's theory of general relativity predicts that time slows down in the presence of strong gravity. Near the event horizon of a black hole, where gravity becomes infinitely intense, time would theoretically come to a standstill relative to an outside observer. This means that if you were to fall into a black hole, you would experience time at a normal rate, while to an outside observer, you would appear to be frozen in time at the event horizon, never quite reaching the point of no return. Some theories even suggest that rotating black holes could create wormholes, connecting different points in spacetime or even different universes. However, the immense gravitational forces and the potential for spaghettification, being stretched into a long, thin strand by tidal forces, make black holes rather hazardous destinations for aspiring time travelers. While the LHC cannot create black holes on a macroscopic scale, it can recreate the extreme conditions found near these cosmic objects, potentially providing insights into the behavior of gravity and time in these extreme environments. Time is not a constant but a relative phenomenon influenced by motion and gravity. Imagine two identical clocks, one stationary on Earth and the other traveling at a significant fraction of the speed of light. According to special relativity, the clock in motion will tick slower than the stationary clock. Similarly, general relativity predicts that time slows down in stronger gravitational fields. While these effects are minuscule in everyday life, they become significant at near light speeds or around massive objects like black holes. The LHC, by accelerating particles to near light speeds, provides a testing ground for time dilation effects. Concepts like wormholes and time travel require exotic matter, a hypothetical substance with negative energy density. This matter, if it exists, could stabilize wormholes, create warp drives, and manipulate time. The Alcubierre drive proposes using exotic matter to create a warp bubble around a spacecraft, allowing faster-than-light travel. While speculative, the LHC could provide hints about the existence and properties of this elusive substance. The creation and manipulation of exotic matter remain speculative, but the LHC's extreme conditions might offer clues. Time travel raises profound ethical and philosophical questions about free will, causality, and history. The classic grandfather paradox questions the consistency and immutability of the past. The potential for abuse if individuals or governments could alter the past is significant. Thoughtful discussions about the potential consequences of time travel technology are crucial before it becomes a reality. While time travel remains a distant dream, understanding time and its relationship to the universe drives scientific exploration. The Large Hadron Collider plays a crucial role in this endeavor. As we delve deeper into the quantum realm, we inch closer to unraveling the mysteries of time. The quest to understand time travel will continue to inspire our imaginations and fuel scientific inquiry. The Large Hadron Collider dissects the universe into its smallest parts, studying the fundamental forces. It accelerates protons to nearly the speed of light and steers them into head-on collisions. These collisions generate subatomic debris captured and analyzed by massive detectors. By studying these particles, physicists piece together a more complete picture of the universe's fundamental building blocks. The LHC operates on a principle similar to smashing two watches together to understand their inner workings. The LHC recreates conditions similar to those just after the Big Bang, providing a glimpse into the universe's earliest moments. By studying particles under these extreme conditions, physicists hope to understand the universe's evolution. The LHC acts as a time machine, rewinding the clock to the beginning of the universe. One key goal is to understand the strong force, which binds quarks together to form protons and neutrons. Studying quarks and gluons at high energies helps physicists understand how the strong force shaped the early universe. Dark matter, an invisible substance, makes up roughly 85% of the universe's matter. Despite its abundance, dark matter does not interact with light, making it invisible to telescopes. The LHC searches for evidence of dark matter particles in high-energy collisions. If produced, these particles would escape detection, but leave a telltale signature. Discovering dark matter particles would revolutionize our understanding of the universe's composition. Some theoretical models suggest our universe could have extra dimensions, hidden from our perception. These dimensions could explain the fundamental nature of gravity and its relationship to other forces. The LHC could provide evidence for these dimensions by producing particles that interact with them. If energy seems to disappear during a collision, it could indicate escape into an extra dimension. The existence of extra dimensions would profoundly impact our understanding of the universe. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. The symmetry between matter and antimatter is fundamental, yet our universe is dominated by matter. The LHC studies antimatter to uncover clues to this imbalance. The Anti-Hydrogen Laser Physics Apparatus ALPHA traps anti-hydrogen atoms to compare their properties with normal hydrogen. Understanding matter-antimatter asymmetry could shed light on the early universe's processes. The universe is governed by four fundamental forces: gravity, electromagnetism, the weak force, and the strong force. These forces are thought to be different manifestations of a single unified force in the early universe. The LHC studies the interplay between these forces and searches for evidence of their unification. By recreating early universe conditions, physicists hope to witness the merging of these forces. Unifying the forces of nature is a grand challenge, and the LHC is at the forefront of this endeavor. The standard model of particle physics explains fundamental particles and forces but leaves many questions unanswered. The LHC searches for evidence of new physics beyond the standard model. By exploring uncharted territory, the LHC could uncover new particles, forces, and phenomena. The discovery of the Higgs boson was a triumph, but our understanding of the universe is incomplete. The LHC's continued exploration holds the promise of profound discoveries. The LHC has made groundbreaking discoveries, but its journey is far from over. Upgrades will increase its luminosity, allowing for more precise data collection. Future colliders, larger and more powerful, are already being planned. These machines will push energy boundaries further, opening new possibilities for discovery. The LHC's legacy will inspire generations of scientists and shape our understanding of the cosmos. The LHC stands at a crossroads where quantum mechanics and general relativity intersect. Quantum mechanics governs the very small, while general relativity describes the very large. These two theories, while successful, don't quite play well together. The LHC offers a unique opportunity to explore this intersection. By studying particles at extreme energies, physicists hope to bridge the gap between these fundamental theories. Imagine spacetime as a vast, intricate tapestry woven from the threads of space and time. Each thread represents a different path through the universe, a different possible timeline. At the macroscopic level, this tapestry appears smooth and continuous, governed by the laws of general relativity. However, as we zoom in closer and closer, down to the Planck scale, the smallest possible unit of measurement, the fabric of spacetime itself begins to unravel, revealing a chaotic, fluctuating quantum foam. Here, the threads of space and time become intertwined and entangled, subject to the strange and uncertain rules of quantum mechanics. The LHC, with its ability to probe the universe at these incredibly small scales, is essentially tugging at the threads of this cosmic tapestry. By studying the particles produced in these high-energy collisions, their properties and their interactions, physicists hope to gain a better understanding of the very fabric of reality. One of the key questions driving this research is whether the LHC's collisions could create microscopic black holes, regions of spacetime so warped that not even light can escape. While these black holes would be incredibly small and short-lived, evaporating almost instantly due to Hawking radiation, their creation and subsequent evaporation could provide valuable insights into the interplay between gravity and quantum mechanics. If spacetime is a turbulent sea of quantum energy, as quantum foam suggests, time might not flow smoothly but could have tiny fluctuations at the Planck scale. These small fluctuations could impact our understanding of time travel and causality. Imagine a tiny transient wormhole connecting different points in time. Though too small for human travel, it shows time barriers aren't insurmountable at the quantum level. The LHC might detect evidence of these fluctuations by recreating early universe conditions. Fluctuations could alter particle properties, measurable by the LHC. Black holes, with their immense gravitational pull, offer a unique testing ground for our understanding of gravity and time. According to general relativity, time slows down in strong gravity, and at a black hole's event horizon, time stands still relative to an outside observer. The LHC might produce microscopic black holes, tiny regions of spacetime mimicking larger black holes. These short-lived black holes could provide insights into gravity and time in extreme environments. As we conclude our exploration of the Large Hadron Collider and its profound implications for our understanding of time and the universe, it's important to step back and appreciate the sheer scale and audacity of this scientific endeavor. Buried deep beneath the French-Swiss border, this marvel of engineering and human ingenuity stands as a testament to our collective desire to unravel the mysteries of the cosmos. Thousands of scientists, engineers, and technicians from over 100 countries have dedicated their careers to designing, building, and operating this incredible machine, driven by a shared passion for pushing the boundaries of human knowledge. The LHC is more than just a scientific instrument. It's a symbol of international collaboration, a beacon of hope in a world often divided by borders and ideologies. It represents the power of human curiosity, our innate drive to explore the unknown and to seek answers to the most fundamental questions about our existence. The discoveries made at the LHC will continue to shape our understanding of the universe for generations to come, inspiring new avenues of research and challenging us to rethink our place within the grand cosmic scheme. Don't hesitate to share your thoughts, questions, and even your wildest theories. Thank you for joining us on Time Pilgrimage, and as always, please remember to subscribe and like.